Hello everybody, welcome. My name is Gail Rajgor and I'm the Managing Editor of Renewable Energy Focus magazine. I'd like to welcome you all to this Renewable Energy Focus webinar presented today in association with Advanced Plasma Power. The subject we'll be discussing is advanced conversion, maximising the potential for energy from waste. Firstly, a big thank you to everyone for joining us today. We have a lot of people on the line, so it's clear the topic under discussion resonates with a lot of people around the world. More of that shortly. Before we start, a couple of housekeeping points. For the two presentations today, you'll be able to follow the slides on your screen. Following each presentation, we will have a question and answer session. You can pose your questions at any time by clicking on the Questions tab on your screen at the right. There you can pose your questions, send them through to us. We'll answer as many as possible, but because we have so many listeners today, I expect we'll get quite a few, so I doubt we'll be able to answer them all. What we're trying to do is follow up with our speakers after the event, and any questions we don't get to, we'll answer later. Okay, so moving on, let's get started. What are we going to cover today? Well, the world is fast approaching a tipping point in terms of the balance between the energy and resources we consume and the waste we produce. The adoption of energy from waste technology still, though, remains limited, despite offering some real benefits. For one thing, there is virtually an endless supply of feedstocks energy for waste plants, and the ability to generate energy from waste is not new in itself and is, in fact, relatively straightforward. For example, there are many different energy from waste processes, but most commonly, waste passes through combustion chambers at high temperatures, reducing it to around 25% of its original volume. Steel tubes that form the walls of the combustion chambers are heated, transforming water in the tubes to steam that is then sent to a turbine to continuously generate electricity. It sounds easy, but despite the simplicity and the abundance of potential feedstocks, energy from waste remains limited. And there is clearly no hiding the fact that the sector faces many significant challenges. For starters, energy from waste as an industry tends to get overlooked by policymakers who favour other bioenergy technologies, not to mention the more high-profile renewable energies like wind and solar. Some forms of energy from waste can be inefficient when compared to other technologies, especially those that are solely used to generate electricity alone. When energy from waste projects are proposed, they can often be greeted with controversy and significant public opposition. So, some of the key questions for the sector include, is it simply that energy from waste has an image problem? Is it suffering from previous bad publicity and a poorly informed public opinion? Is it that policy has failed to provide the right incentives to drive the industry forward? Or has the technology simply got a lot of catching up to do to provide itself with a cost-effective and environmentally viable solution? Let's be honest, no energy technology is without its limitations or problems of acceptance in terms of public opinion. But perhaps more than any others, the key challenge associated with generating energy from waste is to do it as efficiently as possible at a reasonably price, while in an environmentally sound and socially acceptable way on the other hand. If the industry can achieve this, it would go a long way to meeting both the world's ever-growing energy needs while helping to cut down the vast volumes of waste going to landfill. The good news is that some of the newer energy from waste technologies appear to be challenging long-held negative perceptions and achieving some of these aims. In a bit, we'll hear from two experts who give us a snapshot of the current market and some of the technical developments. Stuart Hayward of CTUK will run us through the current state of the energy from waste market, while Rolf Stein from Advanced Plasma Power will bring us up to speed on the company's gas plasma technology. And this uses plasma arc technology to purify waste-derived gas. Gas plasma is an example of one of the newer generation of energy from waste technologies, so-called advanced conversion technologies, or ACTs, that can, according to its supporters and proponents, convert waste into energy with minimal environmental impact on maximising resource and energy recovery. This webinar will look at the development of ACTs, as well as give a snapshot, as I said, of where we stand today in the development of energy from waste. It's a fascinating topic, and one we've been covering more and more in the magazine and on the website, so I'm sure we'll get some excellent insight today from Stuart and Rolf, who are introduced shortly. But first, before we hear from them, we thought it would be a good idea to hear from you guys in the audience. So today, as well as any questions you want to submit to us online, we're also going to have 2 polling questions, which you can hopefully will see on the screen on your right-hand side. It would be great if you can take a minute to consider them when they appear and send us your views. Now, the first question should be coming on your screen any moment now, and it's how receptive is the government in your country to backing or supporting energy from waste as a viable technology? Very receptive, quite receptive, somewhat receptive, or not at all. So just to repeat, how receptive is the government in your country to backing or supporting energy from waste as a viable technology? Very receptive, quite receptive, somewhat receptive, or not at all. You'll find the polling question on your screen, so just make your vote and submit it, and I'll bring you the result later in the presentation. With such a diverse audience from all across the globe, the results should make for interesting reading. So with that first question now out the way, and hopefully a lot of you will be voting as soon as you can see it, we'll move on and I'll shut up. We'll introduce our first speaker, and that's Stuart Hayward Hyam. Many of you may be familiar with Stuart, I'm sure. Stuart Hayward Hyam is the Technical Director of CETA UK. Now part of the Suez Environment business, CETA UK has a long history going back to 1988, delivering environmentally responsible and innovative waste solutions throughout the UK. In 2011 alone, CETA UK managed more than 7 million tonnes of waste through its network of recycling, composting, energy from waste and landfill facilities, recovering and recycling over 2 million tonnes of this. It has also generated over 700,000 megawatt hours of electricity from its landfill gas and energy from waste facilities. Stuart joined the company in 1997 after 10 years in environmental consultancy and was appointed to the CETA UK board in March 2009. He has extensive knowledge of new and emerging technologies, including energy from waste. Today he will discuss the current status of the market, including the barriers and challenges the industry faces, the potential for market development, and CETA's work in the area. Critically, what needs to be done to make energy from waste more viable, and what can be done to win over the public and policy makers, and in the end, increase deployment. So, Stuart, thanks for joining us. Big welcome. Now over to you. The presenter's deck is yours.
Thank you. Hi, everybody. Stuart Hayward, I'm Development Director. For those who don't know, CETA is a waste, resource and energy company. We operate in a number of countries around the world, from France down to Australia and Hong Kong and such. So we have quite a diverse experience of waste from around the world. We develop and operate facilities for disposal, for recovery, for recycling. We operate over 50 energy from waste facilities. We don't own technologies. We're a developer and user. And one of our mantras is that we like to pick the right technology for each project. So we use a multitude of different technologies, and we're continually looking for new technologies, new ways of doing things better. In my presentation, I really want to go through and just help people understand what is waste. It's not like coal, it's not like gas, it varies significantly. It can vary by small municipality and by country. To look at the energy tools that are available today, what we've previously done and what we're doing in the future, and the opportunities in things like electricity, gas, liquid fuels and heat. And to cover off what we want from ACTs, what we'd like, what we think we can get, our opportunities and our concerns. So first question, which is always a question I get asked, is what is waste? Well, waste is what people throw away. And people around the world throw very many different materials away. In Hong Kong, for instance, they'll be doing food and plastic more than they will do paper and card and such. So their waste is very different, and the treatment options to recover energy from those are also very different. So you'll see in this chart a number of different routes down to residual waste. For those who don't know, residual waste is defined by the waste after all the recyclable processes and materials have been taken out. And you can see there you've got food, you've got plastics, you've got wood, which waste wood as a fuel, which we supply as a single stream or may be combined in a residual waste. And obviously with waste and with the feedstock going into waste, it's really important to understand what you've got, to understand which technology you're going to get, what the CV is going to be, how much of that is going to be regarded as renewable, and how much of it will just be general electricity or other energy sources. So if we look at the residual energy waste potential, you can see quite a big range there for the electric and the heat, and that's because waste varies significantly. Some waste will have no CV at all, be it inert or be it fully utilised in some other process. So I'm assuming here the residual waste is something that combines normal municipal or construction combustible waste, commercial or industrial waste. And you can see at the bottom in the graph the current energy mix in the UK, which is my main area of expertise. You can see from the energy produced, electrical energy produced, that at the moment we're dominated by landfill gas, which is the bright green in the graph, and as you can see that dies away because we're stopping putting waste into landfill. You can see on the top of that the turquoise colour, which is the growth of anaerobic digestion, electricity or competing with gas to grid or gas to fuel. And in the middle you can see the orange bars, which go from a dark orange to a lighter orange, which is the difference between actual numbers and predictions. And as with all predictions, they can be wrong, but that's our view currently as to how much generation capacity could potentially be built in the UK. But waste varies considerably, and if you look at the residual energy waste potential, in Northern Europe in the last 2 years, there's been an overcapacity in combustion facilities, and as such they've been drawing in that resource from other countries, such as from the UK, where RDF exports at the moment have blossomed from a few thousand tonnes to currently a few 100,000 tonnes, with over 2 million tonnes of approvals for export. If anything exemplifies the fact that residual waste is a resource, that's it. If you then look at the UK, who started behind most of Northern Europe in their processes, but ahead of other countries in the world, we're moving away from landfill. So the bottom left-hand graph, which I just point to with my pointer, that one down there, you can see the volume of reduction in waste to landfill over the last 4 or 5 years. We've moved something like 20 million tonnes away from landfill. If you then look at the breakdowns, in the next graph across, you've got a combination of food waste, which the UK government is encouraging to go to AD. You've got recycling waste, which we are trying to put back into the circular economy. And then you've got residual waste, which we're looking to recover energy from. And then your third graph is the current state of prediction. So in the UK at the moment, we have nearly 32 million tonnes of energy from waste projects being discussed. We only have about 29 million tonnes maximum of residual waste. So we can see a risk of overcapacity. But many projects won't get built or are competing for particular contracts or tenders, and therefore only one of a number of bidders may actually develop their project. So we predicted that something like 17 million, just over 17 million tonnes of facilities are likely or probable to be built, leaving about 11 million tonnes of capacity remaining, of which about 5.5 million tonnes may well go to EFW style activities. A huge amount of growth in that business. There's only about 9.5 million tonnes built or in build at the moment, so a huge growth. And a large proportion of those planning permissions are ACT type technologies, gasification and pyrolysis. At very different scales. You've got some that are in the 20 or 30,000 tonne range, and you've got some that are in the range of 200,000-300,000 tonnes or more. But we shouldn't be doing this in the absence of understanding the sustainability. And to understand sustainability, to understand what's most important in the swings, and I've picked something that the EU reported in 2001, which is still valid today. So in the table, you can see that we compare municipal waste to energy from waste with no energy, some may call that incineration, to MSW with electricity, or MSW to EFW with combined heat and power. That's heat supply and electricity. And you can see a huge difference in the carbon intensity there. On my graph, the negatives seem to be missing from the lower two, but the first one is a burden, and the second two, the 10 and 348, are net benefits to the system. If you then move down, there's the RDF, refuse-derived fuel, fluidised bed, a different style of technology. Again, you can see the burdens and benefits. And at the bottom, just for reference, you can see what those would be relative to that material being placed in landfill. First set of 3 is landfill, where the landfill gas is collected in a limited way, in a reasonable way, and very best way. You then got the bottom one, which includes or excludes the benefit of carbon sequestration. You can see the influence of that in the process. So you can see it's quite a complex set of calculations that we need to do to understand what the carbon balance is and what we should be achieving. We then look at the current most frequently used technology, and there's over 1,000 moving rate or fluidized bed technologies working around the world. So it's a very well developed and very proven system. If you're just making electricity, the range of technologies can be 18 to 24 with maybe a maximum of 28% efficiency. If you then add CHP, that can go up to 25 to 40%. And CHP plus, which is super CHP, then you can get up to maybe 70% efficiency. So that's the current technology. So when we look at advanced conversion technologies, we're looking for something that adds to that. It adds in either ability to operate at different scales more commercially, or to offer availability of making products that aren't electricity or heat, or to make a more efficient electricity production. If we look at the range of technologies, and I've deliberately not named them here, you can see that on the left under A, combustion steam cycle, that's the sort of range that we get on average in the UK for a moving rate EFW technology making electricity without heat. And if you go then across to B to I, you can see different technologies using different forms of gasification or pyrolysis, some using steam, some using gas engines, some using turbines, and what they achieve in efficiency. And you'll note that some of those technologies are less efficient than EFW, and some of those are more efficient than EFW. And although scale is big influence in terms of whether we very small projects or very large projects, we are tasking all of our suppliers with can they beat that level of efficiency, because that improves and moves our business forward. So what does C2 have a position on EFW? Yes, we do. We think it's a good technology for using recovering the energy from residual waste. We have a project in the UK in Suffolk where we're building a large moving grade technology. That was the right technology for that customer's requirements, the risks, and the commercial circumstance. Conversely, we have a project in London at Charlton Lane where we look to put in a gasification project at small scale and an anaerobic digestion plant. It's a very small footprint site, and it had to be cost effective on a small scale and still meet a risk profile that was acceptable to us and to our customer. And in this instance, we think that gasification is the right technology for this particular project. And you'll keep coming back to this. We're not technology centric. We've picked the right tool for each job. So what do we want from ACTs? Well, I have a wish list. I give my wish list to my wife for Christmas, and this is another wish list for ACTs. We want cheaper solutions at smaller scales. We want to be able to operate on a very local environment as well as large regional environments. We want a more efficient conversion of waste to energy, including the cost of fuel preparation. If you need an RDF, then we should include the burden of that production in the process. And we also want the opportunity for syngas to be used for further products, be it hydrogen, be it fermentation to ethanol or biobutanol, any of those, because that gives us flexibility. What are our concerns? We're worried that incentives make the economics so good that they can ignore the fundamentals of how well things operate. So we like to see whether the technology can run without incentives, as well as whether it can run with them. How well the ACTs work over the medium to long term. It's not a question of whether they work. This is a question of how well they work. In the same way that when a car manufacturer produces a car, the first model may well have a few more problems than the second generation or the third generation. Not a criticism, it's a comment that anything new has a learning curve. We're also worried about gas cleanup costs versus effectiveness and energy production impact. We know that the gas has a number of components in it. We know that we have to clean those up before we can use them in some of the combustion systems that we have. A number of systems which we'll go on to later, but we're important that we understand what they mean, how effective they are, and the burden on the efficiency of the process that they may impart. And on technology choice, why do we want smaller scale? We want to be local to the waste arising. We want to offer the opportunity that a community can have a project scaled for them. We want more potential for local heat offtake, so that we can give them something back in the local community. so we can be local to them, we can be more acceptable in their normal visual environment. We want smaller visual intrusion, and we want to be able to make a better merchant waste fit, because merchant waste is the biggest target we have in this country. And the ACT challenge, I've mentioned it previously, become economic without incentives. That's the challenge, because eventually the incentives will be removed. So don't bank on them forever. Use them to help get through the learning curve and get on and operate without incentives. To improve or prove the availability over medium to long term, that will allow us to use those tools in circumstances where today the risk profile may be wrong for the customer or for us. And this is a plea to be sufficiently humble to understand that they're not always the right tool. With every carpenter, you can use a big hammer and a little hammer, and in these situations, we're very keen to make sure that we pick the right tool for each customer. And sometimes that won't be an ACT. Sometimes it will be a moving great technology, or sometimes it won't even be energy from waste at all. And we have to apply that multiple times. And also help work with us. We're a big company, and we do a lot of what we call industrialization. I use this example. We're just building out a pyrolysis plant in Bristol, which will convert plastics back to diesel and kerosene. We picked our technology holder, and we've worked with them on completing the redesign, making it work better, optimising the design so that it works as best we can make it, and on the fuel creation. And that plant should commission in March. On gas cleanup, there's a number of different technologies, from plasma, thermal, tar destruction, tar removal and scrubber, etc. And we've had various costs for those. And it's sort of proving what's the lowest hurdle you can get that makes your energy production reliable. That's a really big challenge for everyone, I think, to make sure that we can get those sorted. So in roundup, residual waste being used for conversion of energy is a good solution. It's a good for all the countries, wherever you are. ACTs have the potential to be small, efficient, and fill a hole in the market. But they need to be quick, certainly in markets like ours, where build-out is quite rapid. We should all be seeking to make heat, because that makes best use of the energy embedded in the material. And also they need ability to make a product, not just heat and electricity. We want to add flexibility to the system. So that's me done. Thank you very much. I'll pass you back to Gail, who I think is going to pick up some of the poll questions.
Great, thanks ever so much, Stuart. That was a great presentation. And we've actually had questions coming in like there's no tomorrow. But first, before I get to them, we have the results of our earlier poll. So thank you, everybody, for voting there. The question we asked you was, how receptive is the government in your country to backing or supporting energy from waste as a viable technology? And the results are: very receptive, 14% found that their governments are very receptive to energy from waste. 33% voted for quite receptive. Massive 42% said somewhat receptive. And 11% said not receptive at all. So I don't know, guys, if you can come back on the line, but what you think about those results. But I think that's pretty encouraging for energy from waste generally. Just 11% not interested, it seems, and overwhelmingly there's a good response to energy from waste. What do you make of that?
Stuart, I think it mirrors what we see around the world in terms of people can see the potential. There's a slight nervousness. That's probably a very receptive is reflective of a nervousness in the marketplace about how well they work. So getting some more on the ground and proving that they work okay is important to the sector, I think. But no, it's similar to what we'd expect. Okay,
that's interesting. Rolf, any opinion from you?
Yeah, I think it's reasonably encouraging to see that on the whole there's a level of receptiveness. I'd certainly like to know who the A category countries are and see if that tallies with our own information, but no, it's certainly interesting.
Okay, great. Let's move on to some questions here. As I say, they've been kind of flying through the door. I was actually going to ask you a question, if you could maybe explain the difference. A lot of people, when they hear the phrase energy from waste, will automatically think incineration. And I just wondered if there was a difference, if you could explain the difference between incineration and ACT technology. And while I'm there, maybe Stuart, one of the questions that we've had come in from Christopher Moore of the NSL Engine company, actually, Chief Executive there. He's asked if you can maybe explain what you mean by CHP+.
Okay, well, I'll start off then. I think for us, incineration is purely the destruction of waste. Some materials like hazardous waste or medical waste is incinerated. There's no energy recovery. It's really focused on the destruction. Energy from waste of us, the difference, therefore, between that and incineration is the fact that we recover energy and use that energy within either the plant or as an export. With regard to CHP+, that's really about a multitude of different things. That's maybe high pressure steam or supercritical. It may be having a mix of customers where you've got not only primary heat coming from the system, but you've also got waste heat being used in a number of different sources. So optimising your heat uses around you so that you've got the maximum amount of recovery of that energy from what you're pumping out of the system. Okay,
great. Rolf, have you got any different views on the difference between incineration and energy from waste for ACTs?
Well, I guess there's a further step. So Stuart, covered the destruction versus energy recovery and moving great, technologies or combustion technologies, producing steam to generate electricity. ACTs, while some do that, I guess the more advanced are about producing products. So producing a clean syngas stream, a hydrogen and CO stream, which has downstream applications. Not only in on-site power generation, but in the production of other products, whether it's hydrogen or substitute natural gas, or and I'll come on to talk a little bit about that in our presentation.
Okay, great. Another question that we've had just come in from Brian Thomas of Green Energy Development. It's one that a few people have asked actually, but what is CETA's view of using ACTs for medical waste?
I think they have an opportunity because medical waste often is very light and therefore costly to transport. So having very small solutions that work at maybe 5,000 or 10,000 tonnes with an energy recovery component, I think is a real key area that may well develop, certainly in the UK, where we're looking for ways of getting that material used on site or very near to site, where we can give some heat or energy or products back to the hospital or the medical arena. So I think there's a big opportunity there if you can work at very small scale.
Cheers, thank you. Next question, again, it's one for Stuart. Sorry, Rolf. But Stuart, could you maybe tell us what efficiency you expect the Charlton Lane gasification technology to actually achieve?
It depends a little bit on, as I pointed out, on the waste, the final waste mix that we receive, and also we're just in the final process of selecting the technology holder. It won't be at the top end of the process because we're constrained on site footprint and on height. So we're having to fit something very small, and obviously smaller plants, this is only a 60,000 tonne plant, suffer relatively more heavily than the bigger plants on parasitic loads in just operating the plant and the air control equipment and all the other electrical equipment that goes with running these plants. But we're hoping to get a reasonably good level out of that plant.
Okay, great. I think we've probably got time just for one more quick question before we move on. And this one is, what would you consider to be small-scale energy from waste and the smallest plant viable? And that comes from Catherine Warren of AEA.
Viable technically or viable commercially are probably two different answers. Certainly there's some interesting projects at Imperial University and others that are running at very, very small scale, a few thousand tonnes. There's some ACTs running on ships now, dealing with shipborne waste. So in those circumstances, technically they're fine. On a commercial basis, in a commercial environment, as I noted for Charlton Lane, there is a challenge in operating those, and probably that challenge will be met by co-locating them with other niche activities. If you look at our pyrolysis plant, In Bristol, it's about 7,000 tonnes. It's very small in our world, where we're normally talking hundreds of thousands of tonnes. And best for us, we've co-located it with a MRF, and ultimately it's adjoining a plant, a site where we have a gasification permission. So the intention is to hold it under one umbrella of one big site doing multiple activities, and that helps the economics. Okay, brilliant. Okay, we'll leave it there for now, so we can maybe move on, so we can actually, see if we can give Rolf a good say on gas plasma later on. And I hope the audience is interested to hear more about this specific technology, because it's really got some great potential. Now, don't forget to keep sending your questions in. Thank you to those who already have. Some great questions there. Before we move on and actually hear from Rolf, we'll take our second polling question. Again, you need to click on the box on your right to send in your responses on this. The second question is, what is the main barrier to increasing deployment of energy from waste projects? Would you say it's government support, obtaining project finance, and I guess in that regard, in terms of investor confidence, being there in the marketplace for this technology, technical challenges to make energy from waste technology perhaps more efficient, or is it public opinion, getting public buy-in? So to repeat that, what is the main barrier to increasing deployment of energy from waste projects? Government support, obtaining project finance, technical challenges to make energy from waste technology more efficient, or public opinion and getting the public buy-in. So hopefully you've all found that question to the right of your screen, and if you click in the box and send in your votes, that would be great, and I'll bring you the results of that after we hear from our second speaker, Rolf Stein. Rolf Stein has worked in the plasma industry since 2006 and is currently Chief Executive Officer of Advanced Plasma Power. Prior to his appointment as CEO of APP, he was Chief Operating Officer for the company. He joined the company as Commercial Director with a particular focus on securing and commercialising the company's intellectual property portfolio. Before working in this industry, Rolf had extensive international experience holding senior positions in large multinational technology companies, including Hewlett-Packard and Apple. You may also be interested to know Rolf has a law degree, which he gained at University of Warwick, and is qualified to practice law both in the UK and in Germany. So today Rolf is going to discuss APP's gas plasma technology, which is a potential solution to the energy from waste challenge. It's attracted a lot of attention, and earlier this year APP won the Outstanding Green Initiative Award at the Global Business Excellence Awards in recognition of its gas plasma process. The judging panel there said the advantage of gas plasma is that it doesn't burn waste. It turns it into a high-quality fuel gas used to generate electricity. It's a great invention, it's green, and it's just what we need. So that's the view of the judging panel there. Let's hear more from Rolf. So Rolf, a big welcome. The presenter's deck is now yours.
Thank you very much, Gail, and hello to everyone. Really just wanted to give a very quick sort of canter through some of the background to APP, and then come to speak a little bit more about the technology and some of the advantages. So we were formed in 2005, spun out of a company called Tetronics, which has been in existence for around 50 years. We did some proof of concept trials and built a pilot plant in 2005, and then moved to Swindon in 2007 and built our demonstration plant here in Swindon, which is a complete replica of a commercial plant, albeit at a smaller scale, except for the feed preparation front end. So we operate a gas engine and have been operating a gas engine since 2008. We have a very modest objective to be certainly one of the leaders in the waste to renewable energy and fuels market, and are developing a substantial project pipeline around the world, and seeing some very high inquiry levels from specific countries around the world. We're very pleased to have an extremely talented team from both across the technology and engineering space, as well as commercial and project finance and project development, combining those skills to develop our own projects in the UK in particular, where we're taking development risk. and responding to inquiries overseas. We also have a very illustrious advisory board, which is helpful certainly in matters of engagement with political stakeholders and others, which is chaired by Sir John Parker, who's also the president of the Royal Academy of Engineering in the UK, and various other expertise from across the sector, across the industry, including Brian Wilson, a former energy minister, and Bob Clark from the US, who is ex-Westinghouse. In a nutshell, the innovation really is captured there in a quote from Fichtner, who've accompanied our development since the outset. We have produced a gas from waste which is clean enough to use directly in internal combustion engines or in gas turbines, and as I mentioned, have been doing so for some 4 years now. The implications for doing this, why do it? Why go to the effort of doing it? Well, I hope to explain that we achieve, as a result, a greater energy conversion efficiency in terms of electrical power generation. We also produce a clean gas which has multiple applications, so not just on-site power generation through engines or turbines, but a variety of other applications, some of which I'll talk about. And we have a very small physical footprint, which is important in those countries and territories where small scale, where visual impact plays a key role in the planning process. And I'll explain why we are so compact. Turning first of all to energy generation efficiencies, this is a table, not our own, but produced by AEA, that just sets out comparatively the gross energy conversion efficiencies for different power island solutions, starting with conventional sort of steam turbines. As Stuart mentioned, we are seeing some efficiencies now creeping up above that 25% ceiling, but that's sort of pretty much an accepted ceiling, certainly at the kinds of scale that we're talking about in terms of our plant size. Gas engines operating at up to about 41% conversion efficiency. Gas turbines higher still, but with a compression load which brings that back down again slightly. And then really the ultimate goal, the panacea, being the advancement of fuel cells, where predictions vary, but if current development continues, we could see efficiencies of certainly getting into the 70, even up to 80% from gas to power. The next slide really is a summary of the entire process loop as we see it. So the cycle, really both from starting at collection, which of course we're not involved with, but we would receive waste, residual waste, mixed residual waste arising from households or from industry and commerce at our facility, where recyclates would be removed in a feed preparation line, and the residual RDF, refuse-derived fuel, would then be dried using process heat recovered from our process to drive off moisture, which obviously has no energy content. That feed stock, typically our typical plant size is 100,000 tonnes of RDF, which is derived from about 170,000 tonnes of certainly of UK residual waste. It varies obviously according to the waste itself, as Stuart alluded to. That 100,000 tonnes is fed into a fluidised bed gasifier, where a crude or dirty syngas is created and an ash are created. Both of those are fed into a plasma converter, which is a refractory lined vessel with an electric arc being struck from a graphite electrode from the top to the base of the chamber. That electric arc emits a high temperature, but also an intense UV light, and it's the combination of those two facets which are very effective at cracking the tarry organics in the gas stream. The ash is the inorganic components are vitrified into a material which we've called plasma rock, which is an aluminosilicate with a variety of end uses. So we have no waste arising from the process other than a small amount of air pollution control residue, which in itself can be treated, and that is produced in our scrubbing equipment downstream of the plasma converter, which removes particulate and acid gas components such as hydrogen chloride and hydrogen sulfide. That very clean gas can then be fed either directly into a power island comprising gas engines or a gas turbine. It can be further processed into biofuels or into hydrogen, or can be used, or substitute natural gas indeed, or can be used in a fuel cell, either post further processing to produce hydrogen, or something we're looking at, which is to take the syngas directly and use it in high temperature fuel cells. This slide really just very neatly summarizes the effect of the plasma. So on the left of the slide are the tarry organic constituents in a gas being produced by a gasifier. This is our gasifier here in Swindon. And you see relatively elevated levels of the particular species here as toluene, hexane and phenol, which if that gas were fed directly into a gas engine or gas turbine would foul the power island relatively quickly. On the right hand side are the same species being sampled, but after being fed through the plasma converter, and you can see they're really barely detectable levels of the same species, and that gas from a tar point of view is now capable of being fed directly into a power island. The other output from the process, so one is the clean syngas, the other is something which I mentioned we call plasma rock, which we've had tested extensively for leaching in the UK with WRC, and the graph here shows the leachate results from that testing. So the red magenta bars are the inert waste acceptance criteria for inert landfill. Not that we would landfill this material, but it's seen as the benchmark measure. And the purple bars, which you see are the leachate results from our tests. So it's extremely low leaching. We have end disposal options, sale options as a product. We are exploring higher value applications, so it could certainly be used as a secondary aggregate in the construction industry, but we are trying to sort of upcycle that into something a bit more valuable and have some interesting projects ongoing with regard to that. Gasification, really very proven indeed, used around the world to produce syngas for the chemical industry. And there are some, I think it's something like 70,000 megawatts thermal syngas capacity in the world, which equates to about 400 installations, some extremely large indeed. And the technology really was first used commercially in the UK to produce town gas for heating from coke and peat. A little bit on Tektronix, who are our plasma supplier, a sister company. Established 50 years ago, not too far from us in Farringdon in Oxfordshire, and have an extremely extensive patent portfolio for different applications. Have been involved in the supply of around 80 installations globally in all manner of different applications, some of which are set out on this slide. So in the energy from waste context, supplier, the gas plasma arc system, but many systems deployed in Japan for the vitrification of incinerator, bottom ash and fly ash, some at very large scale indeed, 50,000 tonnes per year of ash. Some work in the UK with nuclear waste or these surrogate materials to test the efficacy of the process on treating decommissioning waste from plants being decommissioned, but also waste which is being stored at Sellafield. And it's been shown to reduce the volume significantly and produce a very stable product suitable for long-term geological storage. And then a variety of applications, both in relation to hazardous wastes, where it's more about immobilizing and destroying those wastes, but also material recovery applications. Electric arc furnace dust contains high quantities of chrome and nickel and moly, recovering those metals at stainless steel plants from baghouse dust, but also recovering very high value metals, both from waste electronic equipment, but also from spent auto catalyst and industrial catalyst, recovering platinum and palladium and rhodium and those kinds of metals in very high value applications. A little bit about our view as to the advantages of ACTs, and in particular, our own. We do very much see it as a gateway technology. Waste has a variety of applications, and it should be best used as a feedstock in all sorts of different ways in relation to the particular project. We are seeking to decarbonise not only our power supply, but also heating and transport. And waste has a role to play as a feedstock in all of those areas. So we are, as I mentioned, exploring the use of our syngas in an on-site power generation context, but in fuel cells, high temperature fuel cells, molten carbonate or solid oxide fuel cells, but also the production of hydrogen. Our gas is around 40% hydrogen, 40% carbon monoxide, the rest being water and carbon dioxide. It's very easy to shift to a hydrogen stream, either for use as in hydrogen fuel cells and static cells, or as a transport fuel in fuel cell electric vehicles. We've embarked upon a project with National Grid and Progressive Energy earlier this year to demonstrate the production of what's called biosubstitute natural gas, bio-SNG, from our syngas here in Swindon, and are quite advanced in the engineering of that process, and we'll be looking to build that capability into our plant next year. But as Stuart also mentioned, there are other applications. The syngas can be fermented to produce liquid fuels, or undergo Fischer-Tropsch processing to produce other fuels, aviation fuel, ethanol. So it's very versatile indeed, and the importance, the critical importance, is the production of a clean syngas, both technically but also commercially. That obviously it's done as efficiently as possible. And really, just to summarise the benefits as we see them of the process. So we absolutely embrace the shift to zero waste and produce really no waste products that cannot be processed. The only waste product being air pollution control residues, and that's only really about 1% of the input stream. The other outputs are the plasma rock and the syngas. The syngas with the multiple applications that I mentioned. The system that we have devised and engineered is very much based on proven equipment. So the gasifier and the plasma systems both operate at commercial scale in many facilities around the world, and we have patented this combination in our configuration of gasification and plasma treatment. We very much seek to use waste as a resource optimally to recover as much energy value as possible, but also heat. And in that context, as I said, I'd mentioned that we are a very compact process. We use oxygen and steam in our gasification process, which therefore means we have no inert nitrogen burden in the gas stream. It keeps the plant extremely compact. So we, for a 100,000 ton thermal plant with a 170,000 ton front end, we fit into a site that's around 6 acres in size, a building height that is 10 metres throughout most of the plant, but 15 metres at the thermal plant to accommodate the gasifier, and we have a stack height if we're producing power on site from engines, for instance, of around 10 metres above the roof height, so 25 metres in total, so a very low visual impact. This enables us to locate closer to waste arisings and, importantly, users of heat. We really wish to maximise the potential for CHP by being able to locate close to heat users. And that was it for me. Thank you very much.
Cheers, thanks for that, Rolf. Fascinating stuff again, and unsurprisingly, hate to tell you guys, but a lot of questions coming in for you. Firstly, the results of the second polling question. What is the main barrier to increasing deployment of energy from waste projects? Those results hopefully will be coming up on your screen, but 15% of you said government support, 41% said obtaining project finance or securing investor confidence and the money, 19% said technical challenges to make energy from waste technology, EFW technology, more efficient. 25% said public opinion and getting the public buy-in. So, again, Rolf, Stuart, some interesting results there. Can't say overly surprising to find that obtaining project finance is overwhelmingly seen as the major obstacle. Your views on the results of that?
Stuart, shall I?
Please do.
As you say, I think it is unsurprising in the sort of economic climate that we're in. I suspect it points to a number of the participants being from the UK and perhaps from the West and from USA as well. But the position may be different if the audience were targeted as a Southeast Asian audience. But in the UK, clearly we are developing a number of projects. It is all about putting a commercially attractive proposition together. So, efficiency plays an absolutely key role, and I don't just mean technically. I mean, commercially, it's got to more than pay for itself to go to the trouble of, in our case, making a clean gas to be used in combustion engines. So, that's my first comment: is that you have to put commercially attractive propositions together. It may be that's not achievable with all technologies. I think it is certainly fair to say that there is a constraint in the debt, in the senior debt market, and we think that the Green Investment Bank will have an important role to play in unlocking, particularly senior debt in the UK. But we're certainly seeing a lot of appetite from equity investors to come into this market. And again, there it's about putting something together that is attractive.
Rolf, have you got? Do you agree with Stuart there?
We've another way around yet. Stuart.
Sorry.
I think the challenge of project finance is probably the fact that we attack it in a very linear way between developers of projects, technology holders, waste holders, financiers, equity holders, etc. And I think the challenge in project finance is probably significantly down to getting a good team that cross all of those experiences and making the project and the members in the project working together, in which case you can manage risk. So I recognise the numbers. I think it is UK centric. I think it's also centric of other countries around the world where risk is managed in a singular way. So it's reflective, thankfully, of our experience, and also the challenge is there for us to all work together to make technologies and projects run. Okay.
Before I go any further, thanks to everybody for voting on those two polls today and for sending in the questions. And following on from that poll result and your comments there, guys, we have had somebody from Indonesia send us a question in. And Rolf, they were wondering, would you be able to actually provide project financing with your technology?
So certainly that's how we're going about it in the UK. I think there are, we are attracting equity investors who have interests beyond the UK. We do ourselves have an institutional investor which operates globally. So certainly to some extent, but we'd look to work with local debt providers. And so yes, I mean it's certainly a possibility.
Okay, great. Another question, again relating to that last poll. We've had quite a few people contact us to ask what are financiers generally looking at when it comes to committing capital to such projects, and what's the general view of these guys out there when they're looking at where they're going to put their money?
I think first and foremost, from an equity investor's point of view, is return versus risk. So it's that there are different pots of money traditionally in the institutional investment market, some of which are lower risk, but they're lower return. So, it's finding that balance. And as Stuart mentioned, I think that the whole area of risk management and of passing that off to the appropriate party, in particular, to have single point responsibility in the form of an EPC contract is critical. So it's getting technological buy-in across all the stakeholders to mitigate risk and come up with fundamentally a proposition that's investable for that particular pot of money. That the risks are manageable and the returns are there.
Okay, great. Stuart, earlier you said, and I think both of you guys said that you think that this is very much responses are indicative of a UK kind of centric focus. As I said, we seem to be getting quite a lot of questions coming in from other parts of the world here. And again, another question that's come in is which regions worldwide are currently most active in this particular field? And we have a question here from somebody who's running a development bank, and they're very interested in this kind of technology. So I wondered what your take on that was.
I'll take that first one then. My view, and looking around the world, countries that have a wide vista where their growth in technology, their intent to divert from landfill to make best use of the product are looking at multiple different solutions, and we see a lot of activity in the developing countries, a lot of innovation coming out of the developing countries, which is now being imported to Europe and the UK, in the same way that we've seen from other places. So I think there is a lot of interest. There's a lot more feedstock to go at, which means you unwind one of the risks in the project in terms of making sure that you've got enough waste to run it for the period of your return. And I think there is an appetite to make best use of that in a number of the emerging countries. I think overseas is very attractive. Okay,
and in terms of looking at developing countries and the overseas market. We've had quite a few people come in and email questions regarding fuel sources, and obviously, where you are in the world, the actual feedstock that you'd have for plants varies in terms of its quality, etc. Are there any kind of restrictions there for this particular technology?
Gail, for our technology?
Yeah.
Not really. Well, there will be some, but technically the operating envelope is very, very wide, and we've tested a very wide range of materials here at our plant under different conditions, massively increasing CV, decreasing it, increasing moisture content, etc. Our supplier, the gas-fired supplier, also has extremely broad experience on I think over 200 different feedstocks. But of course, the key to this is building an economic proposition around building a business case around the waste stream as well. So consistency is important because what you put in determines what you get out. But you can engineer and design a plant around a sort of a specific design point. The one that that we have that we vary from according to different projects is an RDF that's derived from pretty typical municipal solid waste.
Okay, great. We've had moving on. I guess looking at, as I said, we've got loads of questions coming in. Another question that's come in is what is the cost addition on a percentage basis of producing biodiesel at a plasma energy from waste plant?
Can't say we've calculated that all the way through, but
how to put you on the spot?
Yeah, there may be better ways, and Stuart can probably talk about certainly a good way of producing biodiesel from a plastic stream. But so we haven't got a fully engineered solution from syngas to biodiesel. I'd have to think about whether that's how that would best be done anyway. But we haven't looked as much at the liquid fuel sort of gas to liquid solutions as we have done and as we are doing on the variety of different gas outputs and gas fuels. But that's not much I can say on that, unfortunately.
Okay. Another question we've got here. Thank you for that. Sorry, I'm trying to rush through because I can see time is really pushing on here. I hope you forgive us. We're going to run over just a few minutes. I just want to get a few more in. This is a question for Rolf. To produce 1 megawatt hour, how many tons of waste would you need?
I'll come back to you on that. I'll just have to work that out.
Okay, no worries on that. And just to let the audience know, any questions we don't get to today, we will try and get answers to you after the event. Let's take another question here. Do you see the electrical utilities working with energy from waste developers for the purchase of the energy created in Europe? How receptive are the utilities for these kind of projects?
I think I'll answer that one. As Suez is part of GDS Suez, so we're a utility as well. We see some interest, but I think there's a mix of interest between meeting whatever the government targets are on alternative energies or renewable energies, and that changes the utilities' interest per market. I also see that of more interest in the UK at the moment is large energy users who actually want to secure their supplies by doing direct supply or cross-grid direct supply contracts where they're looking for a more sustainable or more secure offtake that's not linked necessarily to the gas market or other markets that influence your domestic power supply. So I think they are interested within bounds of what the government has targeted each of them to achieve in sustainability targets or others.
Okay, great. One last question, because we are almost out of time now, if not out of time, but a couple of questions coming here relating to emissions. How are ACTs, and in terms of for you, Rolf, particularly with your technology from advanced plasma power, what kind of emissions are we looking at here? Do you require any EU permits, for example, for projects? And how do the emissions compare, for example, another question here, to incineration?
Okay. So absolutely, you need an environmental permit. What's the Environmental Emissions Directive is being implemented, so that sees sets certain standards. So yes, it is permitted. We do assume that we have to achieve waste incineration directive emission standards, which will be incorporated in the IED, or are being incorporated. So it's not. There's some debate about whether that is actually the right measure, or whether in producing a gas we should be measured against natural gas. But so assuming we will be absolutely WID compliant, are WID compliant very easily. So the emissions levels on organics are well orders of magnitude within those levels. We do produce other combustion products, but keep those to a minimum because we don't have a nitrogen, for instance, a nitrogen load in our process. It's only a combustion in the engine, and we would have a catalyst on the back of the engines to convert any nitrous oxides. So the answer is yes, and we are well within those emissions levels. I do have an answer on the previous question as well, which kind of depends on whether
far away.
It depends on whether you're talking residual or prepared feedstock. But assuming a residual waste input, it's about a 1-to-1. So a ton of waste is a megawatt hour of electricity.
Okay, great. Thank you for that. I'm going to ask one last question because it's been asked by several people again. How many hours per year has the Swindon plant been operating, Rolf?
No, I'd need to look at but we operate on every other week. So for a week, that's the typical, because we share the facility with with another plasma facility. So we'd have to tot up the hours, but that's our operating regime is a week on, week off.
Okay, great. Well, thank you for that, and thank you guys for your presentations. Thank you everybody for joining us today and for sending your questions and for answering those polling questions. Really appreciate it. I think you'll all agree it's been a great session here. I know a lot of you didn't get your questions answered, and we will, as I said earlier, try and make sure that both Rolf and Stuart will be hard at work answering those questions, and we'll get you all responses to them after the event. Again, thank you, Rolf. Thank you, Stuart. Really great session. Thank you, everybody, for joining us. Further details of upcoming webinars will be on our website, renewableenergyfocus.com. This session that we've all just enjoyed will also be up online for you all to go back and look at and see what you missed, etc. And again, any questions, let us know. I'd like to thank you all again for joining us. It's been a great session. This webinar is now ending.